In this video, we're going to look at a connected particles question. So the question states that a caravan is being towed by a car using a horizontal tow bar that's modelled as a light, inextensible rod. The road is horizontal and straight. The car has a mass of 1200 kilograms, exerts a constant driving force of 3260 newtons, and experiences a constant resistance force of 570 newtons. The caravan has a mass of 950 kilograms and a constant resistance to motion of 310 newtons. Both the car and caravan are modelled as particles. Part A asks us to work out the acceleration of the car and the caravan, and Part B asks us to find the tension in the tow bar. The question then states that the driver of the car sees a pedestrian step out into the road. He takes his foot off the accelerator pedal, eliminating the force produced by the engine, and brakes sharply, generating a force of F newtons on the car. The car and caravan decelerate, and a thrust of 130 newtons is produced in the tow bar. The resistances to motion do not change. Part C asks us to find the force F. Okay, so let's answer question 1, Part A. We need to find the acceleration of the car and the caravan. So let's first draw a force diagram to show all the forces acting on both the car and the caravan. We can represent the car as a circle and label its mass as 1200 kilograms. We can also represent the caravan as a circle and label its mass as 950 kilograms. To connect the two, we can draw a horizontal line to represent the tow bar and then label the tension force as T, acting in both directions. There has to be two tension forces in opposite directions due to Newton's third law. Now, for the force exerted on the car by the car's engine, we can draw an arrow facing the direction of motion and label this as 3260 newtons. And to represent acceleration, we can show an arrow pointing in the direction of motion and label this as A. And finally, to represent the resistance to motion forces, we can show an arrow labelled 570 newtons in the direction opposite to motion for the car, and an arrow labelled 310 newtons for the caravan. And because there's no need to label any forces that are perpendicular to the direction of motion, the diagram now shows all the forces we need to consider. So in order to work out the acceleration of the car and caravan, we need to use Newton's second law, F equals ma, where F is the resultant force, m is the mass, and a is the acceleration. This is because we've been given the masses of the car and caravan, and we can also work out the resultant forces acting on them, which means we'll then be able to rearrange to find acceleration. Now, as the caravan has been towed by a tow bar modelled as a light, inextensible rod, we can consider the car and caravan as a single system. So the acceleration will be the same for both the car and the caravan. So the resultant force will be the force due to the car's engine, 3260 newtons, minus the resistance force from the car, 570 newtons, minus the resistance force from the caravan, 310 newtons. So the resultant force is 3260 minus 570 minus 310, which is equal to 2380 newtons. And the combined mass of the car and caravan is 2150 kilograms. And so putting this into force equals mass times acceleration gives 2380 is equal to 2150 multiplied by A. And so A is equal to 2380 divided by 2150, which is equal to 1.107 meters per second. Therefore, the acceleration of the car and the caravan is 1.11 meters per second, correct to 2 decimal places. And so that answers Part A. For Part B, we need to find the tension in the tow bar. Well, because we've got all the forces acting on the car and caravan, and we've just found the acceleration in Part A, we should be able to work out the tension in the tow bar by considering either the car or the caravan. But because there are less forces acting on the caravan, let's consider the caravan. So the resultant force acting on the caravan is T, the tension in the tow bar, minus 310 newtons, which is the total resistance force. And we also know that the mass of the caravan is 950 kilograms and the acceleration is 1.107 meters per second. Therefore, using Newton's second law, F equals ma, we have T minus 310 is equal to 950 multiplied by 1.107. And therefore, T minus 310 is equal to 1051.65. And so T is equal to 1051.65 plus 310, which gives T is equal to 1362 newtons, correct to 4 significant figures. And so that answers part B. For part C, we need to find the force generated on the car after the application of its brakes. So let's draw another force diagram of the car and caravan to illustrate this new situation. This time there's no longer a driving force acting on the car because the driver's foot was taken off the accelerator pedal. So the only forces acting on the car now are the force due to the brakes, which we can label F, and the 570 newtons resistance to motion force, which doesn't change if the brakes are applied. And note that both of these forces act in the opposite direction to the motion of the car. Now, because the driving force has now been removed, this means there's no longer a tension force in the tow bar either, because nothing is pulling on it anymore. But as stated in the question, there's now a new force of 130 newtons in the tow bar called thrust, which acts forwards on the car. Thrust is caused by the momentum of the caravan when the brakes of the car were applied. And so we can label this thrust force as 130 newtons in the direction of motion. But because of Newton's third law, an equal and opposite thrust must also act on the caravan. And so we can label this as 130 newtons acting in the opposite direction. And as in part B, the caravan still experiences the same resistance force. So we can label this as 310 newtons in the opposite direction to motion. And finally, we can label acceleration in the direction of motion, but this will be negative if the engine is stopped and the brakes are applied to the car. Okay, so now that we have our new force diagram, let's try to find the force F. Well, as we've been given the thrust and we've got the resistance force acting on the caravan, we can apply Newton's second law, F equals ma, to find the deceleration experienced by both the caravan and the car. So for the caravan, we have minus 130 minus 310 is equal to 950 multiplied by A. And so A is equal to minus 440 divided by 950, which gives A is equal to minus 0.46315 meters per second. And we can now use Newton's second law for the motion of the car, using the acceleration we've just found. So we have 130 minus F minus 570 is equal to 1200 multiplied by minus 0.46315. And so minus 440 minus F is equal to minus 555.78. And therefore minus F is equal to minus 115.78. And so F is equal to 116 newtons, correct to 3 significant figures. And so that answers part C. If you found my video on connected particles helpful, please click the like button and consider subscribing to my channel where you'll find more A-level maths videos. Thanks for watching.